Welcome to video 14 in a series of introductory videos for InventorCAM. This video's topic is HSM. So the HSM toolpath is a surface-based recognition finishing toolpath. It's a good companion to the HSR toolpath, which is a roughing toolpath, which we saw in video 13. And because of that, a lot of the stuff in this toolpath is the same as HSR. So I'm going to kind of skip over that in this video, but I'll point it out in this video to reference the HSR video, video 13. So let's take a look. So HSM is a finishing toolpath, and each option in HSM is tailored to the geometry that you're machining. So that's why there's so many of the options here. You can see on the left side here. We're going to go through each one real quick. So the first one, if I just open it up, it has the same workflow as we saw in video 13. It has the geometry is set to the target, so we don't have to choose the geometry there. The tool, in this case, I'm just going to use a 1/4 inch bull nose. Constraint boundary is limiting the travel of the tool, and I covered constraint boundaries working areas in video 9, so you can take a look at that over there. The passes section is where you'll see the particular parameters of this toolpath. Now, in this case, we're doing horizontal machining, but if you look in the entire list, each one of these fits a different type of geometry. So horizontal machining only does the flat areas. That's why we only have a offset and not like a step over or anything like a step down or anything like that. It's just going to focus on just doing the flat areas. We have smoothing like we had before, and we can go to the smoothing section and control our radii on that. We can detect the core areas, similar to what we saw in video 13. It's just going to see that if it can come from the side, go around a core, it'll do that. We have Z top, Z bottom. It's just going to travel between those two levels, and that's pretty much it. Now you can control things like the axial offset. You can trim any kind of air cuts, do gouge checking with the edit passes. But generally, this is the same as the HSR toolpath in video 13. It's just for finishing. So in this case, we're only doing horizontal areas. If we take a look at that toolpath, it analyzed the solid and only went to the flat areas of the solid. It ignored everything else. To do everything else, pretty much anything that's completely vertical or has a taper or curvature to it, you're going to go with the constant Z. So again, workflow is essentially the same, constraint boundaries and such. We get the passes, and we have a step down this time. You can detect flat areas, but really this toolpath, as you see here, is really just for the step down. It has a adaptive step down, so you can insert those extra passes like we saw in video 13. And all it's going to do is just focus on any kind of tapers, curvature. You see how it does everything except for the flat area. Linear machining is actually similar to what we saw in video 11 in the HSS toolpath. In HSM, we also have linear. We have our wall offset, floor offset. We have a step over, a step down, a pass extension. So that's similar to the extension we saw in the HSS, which is how far outside the part will go. And we have the angle that we'd like to travel in. So in this case, I have it set to 90 degrees from the x-axis. But because this is a recognition toolpath, it's going to recognize the entire solid. And if we wanted to, we could actually limit the travel of the tool using these angle limits. So it actually doesn't have to do everything. It can kind of just take a look at the solid and eliminate anything that's purely vertical, purely horizontal, and whatnot. In this case, I've done everything. But this is a good example of why I mentioned that each technology, each option, should be chosen relative to the geometry that you're trying to machine. In this case, if we look at the linear toolpath, certain areas, it looks like it might be pretty nice. It might leave a good finish, kind of clean. But if you look at some of these bosses, that tool riding along the side of this boss is not going to leave the best finish. There's a huge gap there, and it's not really tailored to that in particular. So this is why you want to use constraint boundaries. You might want to limit the travel of this tool to only the areas that it looks good, and stay away from these bosses. So you can sketch a line, you can use the edges from the solid to control the constraint boundaries a little further. But this is linear, you just tell it which direction you'd like it to go. In this toolpath, I'm actually going to use those constraint boundaries because, like I said, this is a radial toolpath. Radial machining, you give it a center point, you tell it a max and min radius, and it'll star pattern, spiral, spoke, whatever you want to call it. It does a radial toolpath out and in from that center out to a max radius. Now, that doesn't make sense for a part like this. This part is square. It has different bosses and features. A radial would not look good other than only in this dish section. So in the constraint boundaries, that's what I've done. I'm limited it to just the dish area. I've actually added all the edges of that particular surface so that I don't even bother doing this flat area. Because for the star pattern, I don't really care to see what it looks like in the center. I just want to have a toolpath that just does the dish. And that's the use of the constraint area just to limit the travel of the tool. Just what I want to finish. Now, that could have also been done with an HSS. It depends on which toolpath you're more comfortable with or which one has more control over what you're looking for. On our YouTube channel, there is a video called HSM versus HSS that you can take a look at to see when you would use HSS versus HSM. Spiral, same sort of thing. I use the constraint area to just do all of the dish, including the flat area in the middle. And what this does is it lays down a spiraling toolpath, similar to what we saw in video 12. I've just told that the constraint boundary is the upper edge of that surface, that just basically that complete circle. I tell it a center, a max and min radius, and it lays down the spiraling toolpath. If we take a look at that, you can kind of see that it lays down the toolpath even in that gap there. Morphed machining, similar to morph between boundary curves like we saw in video 12, is the HSM version where we give it drive boundaries, in this case, a start curve and an end curve, and then we constrain the movement of the tool to just that one surface. So it's going to blend between the start and end curve just along that surface. It's still a surface-based toolpath, but by giving it a constraint boundary, I'm basically telling it, apply this toolpath but to only that one area in between that sketch. And we have a step over. So all that's really going to just generate is a toolpath on that specific surface that blends between the one side and the other side. So this is a good way, again, to finish just one particular area with a toolpath that matches the geometry. That's something that will leave a good finish. Offset cutting is a similar idea. So offset cutting is similar to parallel to curve, like we saw in video 12, where I give it a drive boundary of just a single curve, in this case, just that edge there. To the right of that curve, the right of the left, the white arrow there, so on the right side of that arrow, we're going to go along there, or we could do perpendicular to that as well. So this is a combination of perpendicular or parallel, depending on which one you want to use. Constraint boundary, I'm doing the entire solid, but in the passes section, I can tell it how far parallel to that line I want to step over. So this is a similar toolpath to also what we saw in video 6 in the profile, where we're doing a clear offset, and it's similar to the video 12 HSS parallel to curve in that we're giving it a curve to follow. So this is one toolpath that you can consider does all in one. And all you're really doing here is just choosing one edge, and as long as the features on that solid match that edge, you'll get a nice finish. And again, this is another good example of limiting the travel of the tool, because I probably don't want to follow this as I go along. It's going to get a different looking toolpath as we go along. Probably not going to like it too much. Boundary machining is similar to projection, again, from video 12. You'll see that there's a lot of similarities between HSS and HSM. One is surface-based, one is solid-based. This one being solid-based is really good for projecting some sort of sketch or logo or text onto a part using a drive boundary. Now, if I show my drive boundary, you'll see that I've added a sketch. I tried to add some text. Now, to be honest, I'm not the best at Inventor, so that's why I kind of just did it as a series of lines. So it's a good example of the fact that it's just any sketch you throw on there, and it's a good way to avoid doing projections on the design side. So if you're not if you're not really good at Inventor, like me, or if you're working with our other product, SolidCAM, and you're not doing, you don't want to do projections inside SolidWorks, anytime you don't want to do any kind of real projection, any kind of design work, sometimes you can rely on the toolpath to do it for you. In this case, that is a planar sketch. If I just show that sketch, I didn't do any projections. That is just a simple planar sketch that I've projected onto the part using only the toolpath. So if I hide that guy again, and we open up the toolpath, I set that, again, as my drive boundary. I just told the tool to follow the center of the tool along that curve, or that sketch. I'm doing the entire solid, but only because I want to project it onto that solid. And you see that boundary machining really doesn't have anything else in here. All it's going to do is just project that sketch onto my part. So it's a good way to do 3D engraving. 3D constant step over is one of the more powerful toolpaths inside of HSM. Again, it has a drive boundary, so I'm just giving it something to follow. In this case, it's just that circle. So I'm going to offset from that circle, and I'm using the same circle for my constraint boundary. I don't want to do it for the entire part. I just want to do it inside that circle onto the face of the part. So again, it's sort of a projection of this offset step over onto the part. If we take a look at the toolpath, again, it's offsetting what kind of looks like a spiraling, but it's really more of an offset from that drive curve. So if you wanted to do the entire part, you could choose the outside edge of the part, offset from the outside edge of the part, and you would get a 3D toolpath across the entire part. This is a toolpath that if you don't know which one of the other options to use and you just need to get this thing finished and you're not really concerned with cycle time, you could use this one. We do a simple step over from the outside edge of the part and work its way inwards. 3D corner offset has a similar function. It just has different initiator sites, and it doesn't really have a, let me just open it up here. It doesn't really have a drive boundary. Really, it's all you're going to do is just give it step over, step down, and then just do the entire part. So this, again, is a one that you can just kind of use like a hammer instead of a scalpel and just finish out your part as much as possible. Now, pencil milling really is only for the tight areas of the solid. It's still using the target as the geometry. In this case, I'm using a 1/8 ball nose. Constraint boundaries, I'm just doing the entire part. And under passes, all you're really setting it here is a bitangency angle, the angle that the tips of the tool make with the corners. So if the angle made by the normals of that surface and that surface in that corner is this or less, then it considers it to be a pencil area, and you get a toolpath that really is just a single pass along all those tight areas. So it's just kind of a corner cleanup kind of toolpath, pencil milling. Parallel pencil milling is that same idea, but with a bit of feathering out. So you can actually open up the toolpath here and take a look at the fact that I can give it a step over and a step down and number of step overs and step downs. So it's really just that continued feathering of a pencil operation, pencil milling. And then lastly is the rest operation. So again, like all the other toolpaths we've seen in this introductory series, anytime we're calling out for rest, it's asking for us to finish the remaining stock. So whatever the previous tool did not do. So this tool is the 1/8 ball mill. The previous tool, I'm telling it was a 1/4 inch ball mill, and it has similar controls to the parallel pencil milling. I'm just giving the bitangency angle so I can recognize tight corners, and a step down and a step over. And knowing that there is a previous tool, a reference tool, I can get it to edit outside the air cuts and such. But really all it's going to do is just analyze based off of those parameters. If the previous tool was used, where did it not touch based off that tangency angle that the previous tool would have made? And here you go. You get a similar kind of feathering out, but this is more for removing material that would have been left behind by the reference tool. Any questions of this or anything else from SolidCAM, just give us a call at 1-866-975-1115 extension 2. You can send us your parts or your questions via the ticket system at solidcamsupport.com. And stay tuned for the rest of the videos in this introductory series. Thanks for watching.